Hello, calculus fans. Let's talk about curl and divergence. So these are two operations that are defined on vector fields, and they're very important in the context of fluid flow and electricity and magnetism. These are analogs of derivatives. They're types of derivatives. One of them is going to produce another vector field, and the other will produce a scalar field. So the input is going to be a vector field. One operation turns it into a different vector field. Another operation turns it into a scalar field. Let's suppose that we have a vector field F, and it has components P, Q, and R. And let's just suppose that the partial derivatives of P, Q, and R all exist. Then we're going to define the curl of F like this. So the curl of F is another vector field. The I component is dr by dy minus dq by dz. The j component is dp by dz minus dr by dx. And the k component is dq by dx minus dp by dy. Okay, the chances of me memorizing this are slim to none. So what we're going to do is create a convenient way to remember this. So to that end, let's introduce a vector differential operator. And we've actually seen this before. It's the del operator. So this vector differential operator is I times d by dx plus j times d by dy plus k times d by dz. It's just an operator. It's not really an object. And this operator will have meaning when it operates on a scalar field, and it will produce the gradient of f. So del f is equal to I times df by dx plus j times df by dy plus k times df by dz. So that's the gradient, and we've used that in the past. Now we can also think of del as a formal vector. So it's not really a vector, it's kind of just a formality. The components are d by dx, d by dy, and d by dz. You see, a vector, really, the components should be objects, whereas here we're thinking of the components as being verbs, things that take action. So when you write d by dx, that means compute the derivative with respect to x. What we're going to do is create a formal cross product of del with the vector field f, and it's going to look like this. So we're going to compute del cross f. So del has the components d by dx, d by dy, and d by dz. And then f has components p, q, and r. So when we compute this determinant, here's what we get. Okay, so you can work out, say, the I component. How does that work? Well, you take this determinant here, and that determinant, what you're doing is d by dy of r. So that's dr by dy minus dq by dz. And if you do that for each one of these pieces, then you're going to end up with the expression that you see here. And if you go back and look at what we had before, this is the curl of f that we've defined previously. Take care to note that here we're writing it with a minus because it came out of a determinant. When you go look at the one before, it didn't have a minus sign, but on the other hand, the expression that we had before, these two were backwards, so it really is the same thing. So we're going to remember the definition of the curl by writing curl f equals del cross f. So it can be computed using this sort of formal cross product. All right, let's do a quick example. Given this vector field f, which has components x, y, z, negative 2x, and y, z, let's compute the curl of f. So, as we've discussed before, the curl of f is computed by putting the ijk in the top row, the del components in the second row, and the components of f in the last row, and computing a determinant just as we always have. So it's a kind of a cross product. And if you work out each piece, so the I component is d by dy of yz minus d by dz of negative 2x, and so on. Each component is computed as you normally do with a cross product, except it's not really a multiplication now. It's an operator acting on some function. And if you work all this out, you'll end up with z, xy, negative 2 minus xz. Notice that the end result is another vector field. So we started with a vector field f, and we got a new vector field. So the curl takes in a vector field and gives you a new vector field. Okay, that's all for now.